All right, people. Today I'm going to talk about tsunamis. This is a paper by Hammack in 1973 studying the generation and propagations of tsunamis. So let's start with the question of what is tsunamis? They're waves generated by submarine earthquakes, and they have large typical wavelength. They have large wavelengths with small wave heights compared to the ocean depth. And in this paper, the problem is only confined in a two-dimensional fluid domain with uniform depth and infinite lateral extent. And this paper gives out an integral solution. For a quick visualization, this is the setup where you have the infinite lateral in 2D. The zeta function defines the ocean bottom, the solid boundary, and the eta function defines the free water surface, and they are both functions of space x and temporal t. And the depth of the ocean is lowercase h. And the integral solution is developed for arbitrary given bed displacement, and the author has used a linear theory to linearly approximate the boundary conditions to derive this integral solution. So one of the key question in this paper is to study whether this linear theory or when is this linear theory applicable. Okay, the conclusion, a quick conclusion here is that the total amplitude of bed displacements remain small compared to the uniform water depth, and it can be relaxed, in fact, for creeping bed deformation, which means slow bed deformation in the end. So let's start with the equations. Here's the setup for the continuity equation, the boundary condition on the free surface on the ocean bottom, and the dynamic condition based on inviscid flow and negligible surface energy. We have three boundary conditions and one continuity equation. And the linear theory comes in to kill the nonlinear terms, and the nonlinear terms, so that we arrive from equation 2, 3, 4 to these three linearized boundary condition. And then we combine 5 and 7 together to arrive at 8, so that we do a Laplacian transforming t and Fourier transforming x for equation 1, 6, and 8 to arrive to this form, where the over bar over a function is defined as an operator as follows. You have the Fourier transform and the Laplacian transform. So that's the operator. And you plug it in the boundary conditions linearized into the continuity equation. You have the free water surface function to be explicitly expressed by the bed deformation function, while transformed in Laplacian temporal variable and Fourier spatial variable. By this point, the author argued that we can no longer facilitate or no longer improve the conclusion unless we give out explicit bed deformations. So we introduced two deformations. One is called exponential bed movement, and what the other is called half sine bed displacement. And they're defined as equation 18 and 19. To visualize it, I made a Python movie where the blue line with the same parameters, the blue line represents the exponential bed movement and red line represents half sine bed movement, so that we can see that with the same parameter, the exponential moves way quicker. So that's the reason why it's called impulsive bed deformation, and the slower the half sine bed movement is called creeping bed deformation. All right. So with these explicitly written out zeta function, we can plug it back here to arrive for the eta function. So the explicit form of the eta exponential and the eta half sine are written as these two functions. They're not very beautiful, but they can be numerically integrated, which I also did. Here, initially the free water sea surface is flat, and then the exponential bed deformation at bottom gives it the a rapid motion of the exponential free water surface, and this corresponds to the half sine, the creeping bed deformation. They have a slower deforming, and they have actually smaller wavelengths, which will be also studied later. Now, to distinguish, as I said, there's a fast exponential movement and a slow half-sine movement. So how to distinguish the fast and slow is defined by a characteristic time here, Tc. Tc characteristic time is defined when the total elevation or the deformation has gone 2/3 of the total displacement. So total amplitude of deformation is called zeta naught. So when the zeta is 2/3 of the total zeta naught, we call it the time to the characteristic time. With this characteristic time, we also write out the momentum equations and continuity equations and the boundaries. With these five explicitly written out equations, we have the characteristic vertical velocity. The characteristic, the non-dimensional term is zeta naught over the characteristic time, the total amplitude deformation. And then based on that, we do the non-dimensionalization. And we written out the momentum equation, the continuity equation, the boundary conditions as follows. And we arrived at the coefficients for the non-linear terms. The first one and second one, there are coefficients. For the non-linear momentum equation, the coefficients must remain small so that we can kill the non-linear terms. So we can see the terms here. These five equations are for the impulsive, the fast boundary, the fast bad deformations. So these two terms must remain small so that we can kill them to apply the linear theory. So this arrives here. That for impulsive bad movements, this is the criteria for how to define impulsive and creeping, which means fast and slow, is defined by a time size ratio defined by characteristic time square root gh over b, the width of the bad deformation. So if the time size ratio is small, we call it impulsive, which means fast elevation or fast downthrow. And we have these two terms must remain small. Similarly, for creeping, which means the time size ratio is large, we do the same method for non-dimensionalization. We write the coefficients for non-linear terms must also remain small. So here the time size ratio is large, so the reciprocal of it must remain small. So similarly, we have these two terms must remain small, and by doing it, we have zeta naught, which is the total elevation of the bad deformation compared with the ocean depth. They must remain small for both cases. Then after this theory, we arrive into an experiment designed by the author, where this part resembles the bad deformation using a bottom wave generator. And to dissipate the energy, we have the downstream end, which is not shown here. We have a wave energy dissipation system. Just to study how good is this linear theory and using the non-dimensionalization, how the criteria are followed. So the first, they look at the region at the center, when x equals to 0, and then they look at the downstream edge, which is the far right end of the x equals to b, where b is the width of the deformation. And in this graph, for at the center, we can see that this is the time size ratio. This is the response. Eta naught is the amplitude of the free sea surface. How the order of the response is responding to the total bad elevation, the amplitude of it. And then the straight line here is the linear theory, and the dots are observed by experiments. We can see that it's very good fitting. And for small time scales, for the time size ratio being small, which means the impulsive, we have the relative wave amplitude to be constant. As the time size ratio grows up, it becomes inversely proportionate, and which corresponds, the experiments agrees with the theory, and which is described here, constant and inversely proportional. And the nonlinear effects becomes very significant for impulsive, which means the time size ratio is small, and transitional, which means the time size ratio is around 1 when the amplitude of the elevation is large compared to the ocean depth. So about more than 1/5 of the ocean floor of the ocean depth is being elevated or down thrown. So that's the examination on linear effects. And it is worth noticing that for the creeping, the large time size ratio, the non-linear effects is still small. And this is the graph for x equals to b, where you can also see that the linear theory and experiments fits pretty well. Then we're looking for the wave profiles that is at the generation region, so which is in negative b to b, that is saying that for impulsive back motion, the water initially moves to a maximum displacement at zeta naught when at the center, and half of the total amplitude of elevation at the downstream edge, which agrees here, as you can see, that when I go, reaches to the maximum, so the maximum of the zeta naught and half of the zeta naught at the edge. And then it grows up, and then it comes to a certain point where it becomes the water level remains stationary for an interval of time. Stationary. And then returns to still water level with oscillations in damped manner. So goes back as the 1 and 1/2 relation, becomes still, goes up, but damped oscillation eventually being diminished. And then the author also said for the impulsive motion, the final shape of the deformed bed is not dependent on the time displacement history of the bed, yet compared to the creeping bed motion, it is significantly determined on the bed displacement history, which is for the right-hand side of the graph. The wave is dependent on time displacement history. And in contrast, where I did not graph, but for transitional bad move motions, it follows with the going to maximum displacement, and then it immediately returns to the still water level, which do not have this stationary for an interval of time, the halt. And this is also the experiments versus theory, the linear theory, the measured. You can see how good it fits, the time size ratio without dividing by b, and eta over zeta naught, the elevation of the water surface over the total amplitude of bed deformation. So we jump right to the conclusion of the experiment, how it fits with the linear theory. And so for impulsive bed motions, the initial wave structure resembles the final shape of the deformed bed, except the time display history does not really matter. For creeping bed motion, it's strongly dependent on the time displacement history. And the research goal, the nonlinear effects, are observed to be significant at the downstream edge, the far right edge of the deforming width, only for impulsive or transitional bed motions where the time size ratio is smaller or equal to 1, and given the bed displacement must be exceeding 20% of the total depth of the ocean. So here's the conclusion here I've written. For impulsive and creeping, nonlinear effects becomes when the elevation is large and no dependent time displacement. This is the applicability of the linear theory, and that's the same thing for creeping back movements. Then the author dived into the examination on nonlinear effects, where he also introduced a characteristic length of waving proportion, a direction of propagation defined by L. So there's a ratio called U, is the ratio of nonlinear effects over the linear effects. Arguably is that for small u, the linear effects dominates. For large u, the non-linear effects dominates. Yet sadly, there is a explicit form by given certain initial condition, which is flat, bottom flat surface, is that the non-dimensional ratio of nonlinear effects grows up like 1/3 power of time. So eventually, nonlinear effects becomes very significant. And to model this propagation on the downstream edge, the author has argued that we can consider using the KdV function or also a PBBM equation. So these are the conditions of settings of using it. So integrating on X is about the total net wave volume from the far left end to the far right end, and positive and negative implies net positive volume and net negative wave volume, which is critical in using PBBM equation, because in the end, the conclusion is that only the positive net volume can be applied with it. So let's skip this part right to some visual thing that also the experiment was done in O'Leary frame, which is trivial because you are using cameras. So O'Leary. So this is the visualized conclusion using PBBM, using linear theory, and the actual experiment. So how they differs, and this is the applicability of using PBBM equations to model the propagating downstream waves of tsunamis, where u deviates by x minus b. So now you have a right propagation, and you can see that for this case, but only for this case, this is effective. What do I mean by only this case is because when you're having a downthrow, the PBBM does not really models the significant changes here. So it was said in the conclusion here that the PBBM provides a satisfactory model of wave behavior, but only when the bad deformation is such that the net wave volume is finite and positive. So not really working for negative, but it still remains to be a working model using PBBM for the downstream wave propagation of tsunamis. So that's probably it.